Let's talk about linear regression. What is the problem? Given a list of points, let's have an example. Let's have this list. In this case, we have 6 points, so n is 6, and the a coordinates are these, and the b coordinates are that. Let's plot a scatter plot. And now the points 1, 2 is this point, 3, 2 is this point, and so on. These are the 6 points in the scatter plot. And now what are we looking for? We are looking for a straight line which fits to the points. So for example, that line. And how is that line described? The line is y equals to some slope, let's call that m, the input argument x, and some value here plus c. And what we are looking for is some adequate m and c. And how can we compare two different suggestions? We can measure the deviation. We sum up over all these 6 points, and then we take the x-coordinate, m times the x-coordinate, m times a1, a2, and so on. So ak plus c. This is the value on the straight line. This one, this one, this one, and so on. And then we take the difference to that point. So that is bk. So we have these differences. And because it's more easy to do the calculations, because of that, we square that difference. I think that this is introduced only because the calculations get more simple. So using that, we measure the differences. So that means we take the square of these values. And then what do we want? We want that this value is as small as possible. We want to minimize. Okay, let's have an example. Let's use, for example, m is 0.5. So this is the slope. C is 1. And now we measure the deviation. So we take that. So 0.5 times a1 plus c minus the value this one, and then square that. Then plus again 0.5 times 3 plus 1 minus 2 plus, and so we go through that list, and 0.5 times 9 plus 1 minus 5 squared. And if we do that calculation, we get a value which measures how good does this straight line fit to these 6 points. So what is that value? We can do that calculation by hand, but we can also use electronic help. Okay, here I entered the points. The first column represents the a values, and the second column of AB represents the b values. Then we can plot these points, and then we can say, okay, let's use the slope 0.5 and let's use the c value to be 1. And then we take all of these points and we calculate m times these points plus c, and then we subtract the b value, we square this deviation, and then we sum all these deviations squared. Let's run that code. And here we see these are the a values, the b values, this is our assumed m and c, and then we get the sum of the deviation to be 3.75. And we have a plot. This is our plot of our 6 points. The y-axis starting at 2. In our sketch we started at 0, and here it ends at 10. We ended at 9. Okay, so we have the deviation 3.75. Okay, what do we want? We want to find a better m, a better c, which fits better. So a less sum is produced. That's what we hope. So what can we try? Let's try slope 0.6 and let's test C is maybe 0.8. And then we measure the deviation by 0.6 times 1 plus 0.8 minus 2 squared plus 0.6 plus 0.8 here, and then our points, so 3 and 9 and 2 and 5. Let's check which deviation we get now. Okay, so let's exchange 0.6 and 0.8. Now let's run that code. And now we get the value 4.92. So this choice was the better one. And what are we looking for? We are looking for the best choice. Okay, but how can we find the minimum? Let's introduce some writing. And with that writing, we are looking for a times x minus b gets minimal measured in the Euclidean norm. Why is that really true? Let's see. So we can write that way. And now, what is that product? That product is m times a1 plus c minus b1 in the first coordinate and in the second coordinate. And taking the Euclidean norm squared is what? So the whole thing is that. So indeed we are looking for the x which fits best. And so we are back in the context of our overdetermined systems. So we want to find the x fitting best. And what does that mean? What did we learn in the last video? This is our equation and we have to multiply by A transposed. I explained that in detail in the last video. So for finding that x, we can use MATLAB, Octave or something like that. And this is a quadratic system and we need some solver for that system, and so the job is done. But in this specific case, A transpose times A, we will get a 2 by 2 matrix, and here we can continue our analysis. Here, specific in the context of linear regression, we can analyze a little more in depth. Okay, so let's do this analysis. What is A transpose times A? A is that matrix, so the transposed is. And what do we get? We get a 2 by 2 matrix, and the entry here is a1 squared plus a2 squared plus and so on plus an squared. And so it's the sum of the ak squared. And what is that entry? This times that plus and so on. So this is the sum of the ak, and it's a symmetric matrix we learned in the last video, so we have this entry again. And here we get 1 plus 1 plus 1 plus 1, which is n. And now the right hand side. Then we get a 2 vector, 2 entries. And the first entry is a1 b1 plus a2 b2 plus and so on, an bn. And this entry is b1 plus b2 plus and so on. And so this system is times x. And so we have this 2 by 2 system. So whichever n is, if n is 6 or n is 10 or n is 1000, this is always a 2 by 2 system. And we can get the solution of that by multiplying with the inverse, and 2 by 2 systems, the inverse is not that complicated. If we have a matrix D, E, F, G, and we want to find the inverse, This is not that hard to do. Let's swap these entries and let's minus these entries. And don't forget to divide by the discriminant, so dg minus ef. And this is the inverse, and now we can multiply with that inverse. Multiplying with the inverse from the left, we get the inverse of that, which is swap these two entries and minus these entries. And don't forget the discriminant, which is that times that, minus that times that. And we have that vector. Okay, what is the entry m? It's n times that plus that divided by that. N times that plus that divided by that. And that's our m value. And our c value we get by that times that plus that times that divided by that times that times that. Let's start with that, it's more elegant when writing down. And then this minus divided by that value again. And this is how we have to choose m and c. And all what we wrote down here is to be wrote down only once in history of mankind, and this is our solution we can use. Let's go back to our example in the beginning. What were the values? Here these values are ordered, but that is not necessary. And now first we need all these sums. We need the sum of the AK. This is 1, 4, 8, 14, 22, and 31. The sum of the BK, 2, 4, 8, 11, 17, 22. Then the mixed products, 2 plus 6 is 8, plus 16 is 24, plus 18 is 42, plus 48 is 90, plus 45 is 135. And then we need the squares of the AK. So it's 1, plus 9 is 10, plus 16 is 26, plus 36 is 62, plus 64 is 126, plus 81 is 207. And we don't need these values squared. So how to choose m? It's 6 times 135 minus this product divided by 6 times, this was squared, 207 minus AK 31 squared. Don't confuse that with that. So if you do that calculation, what value do we get? If we are using electronic help, it will tell you 0.4555. Okay, and how to choose C? C is 207 times 22 minus 31 times 135 divided by that. And using electronic help, you will be told 1.3132. And that means the values of m and c are to be chosen. And then we get the minimal distance. Let's do these calculations. And then we can compare if we choose these values, if we get better than 3.75. Theory says we must get better. But okay, there could be some error, so let's check. So let's redo our calculation. Let's check our values. Sum of A is 31, as we said. Sum of B is 22, as we said. Sum of the mixed products is 135 as we said. The sum of the squares is 207 as we said. And so our m is to be chosen. M is and we get, as we said, 0.4555, and C is, and we get 1.3132. So with that choice, we can comment that out, and then we can check this sum of the deviations, and then we can check if we get better. So let's do that. And now the sum of the deviation is 3.6157. And this value is a little less than that value and much less than that value. And it's impossible to get closer to zero with whichever values you are choosing. These are the optimal ones. We can also revisit our plot, and let's draw that line into that plot. So let's say the x values for our plot are 0, 10, and the corresponding y values are m times x plus c. And then we can plot that. So hold on, plot x, y, and let's plot that line in blue color. And so here we see our line of regression, which fits best in the sense that these deviations here, straight lines from here to the line, if you square that difference and sum these, then you get a minimal value. Every other choice of m and c, so every other line, will produce a larger sum. So now we are done, but I want to show you one more thing. Let's go to Excel. I entered our 6 points, and then we can do the XY plot. Okay, sorry, this is the German version. I hope that does not confuse you. Okay, this is our scatter plot, and now we can mark these points, right click to one of these points, then in German version Trendlinie hinzufügen, the linear trend, and show the formula in the diagram. And what do we get? We get here the line of regression, and the optimal choice of values is 0.4555 plus 1.3132. That is exactly what we calculated also. So also in Excel, this line of regression is also available to be clicked. And what's happening in the background, it's the calculations I showed you are done in the background here in Excel. So that's all. That was our video about linear regression.